So what is planar defects? Planar defects are imperfections in the arrangements of atoms within a crystalline material that occur along a specific plane.
This defect disrupts the regular periodic structure of the crystal and are two-dimensional. I mean two-dimensional in nature. Unlike volumetric defects which are three-dimensional, such as twin boundaries. A crystalline free surface refers to the exposed outer boundary of a crystalline solid, where the ordered lattice structure of a crystal abruptly ends, essentially creating a crystal or a surface with broken atomic bonds and different atomic structures compared to a bulk crystal. So basically, it is a free surface that is exposed to interact with the surroundings. In material science, a free surface refers to an unconstrained external surface, where this is the external surface, while the free surface of the crystal is not in contact with any grain or atom of the same crystal. So the atoms that are exposed on the free surface may undergo changes or reactions such as surface energy effects, since it is exposed to the environment. It can influence properties such as adhesion, diffusion, and surface reconstruction. Other examples of free surfaces and their effects in our daily lives are the metal surfaces of coins, mirrors, and salt and sugar crystals.
What is a twin boundary? A twin boundary is a special subset on grand boundary in which atomic structure on one side is a mirror image to the structure on the other side.
In this picture right here, so it looks like if this dash line, which is we call our twin boundary, if it was a mirror, that's exactly what we would see from this side to the other side in this picture right here.
So the other thing that we should take note about this boundary is that it doesn't look like the atoms are in this order here. So in fact, usually, the twin boundaries are called coherent. So let me explain to you an example about coherent twin boundaries.
I'm going to explain about coherent twin boundary. So coherent twin boundaries are areas in which the material internal structural pattern forms a mirror image of itself along a shared border. So actually they occur when crystal formations on either side of an atom-wide border line up without disorder. So basically, those lattice structures just happen to match up along the boundary. So now I'm going to talk about results when stacking sequence of plane is reversed. So, twin boundary result when the stacking sequence of the plane is reversed. So let me give you an example in FCC. If we have an untwinned FCC material, then the stacking sequence is ABC, 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 right? Where A, B, and C are the different plane locations. And then if we twin that, if we twin FCC, it goes ABC, ABC. As you can see, B could be connected to A or C in this case. So we go from ABC, ABC. The next one normally would be an A, but it could be a B. So we connect it to the B and then we reverse the order. Okay, which is what you actually see up here. So let's move to EBLSD, that's electron backscatter diffraction. So twin appear as straight lines running across the grain, this one, just like this. We can see this very straight line kind of going across. So those are example of twin boundary, this one. One more type of defect that's related to a twin boundary but it's distinct from is called a stacking fault. For the FCC, we go ABC, ABC. Then instead of C, we go back to A. But the crystal still repeats, so it's not a mirror image. So let's move to
about what is line defect. Line defect is discoloration. It's a type of imperfection in the crystalline structure of a material. These defects significantly affect the mechanical properties such as strength, ductility of a material. So what is mixed discoloration? Mixed discoloration is kind of combination of two discoloration. One is edge, another one is screw. Okay, let's be specific. What is edge? What is screw? Okay, at first let's talk about edge. Okay, edge is actually characterized by an extra plane of atoms inserted into the crystal structure, and this will cause localized distortions. So this is edge discoloration. So let's take a look about screw discoloration. Screw discoloration formed when a part of a crystal structure, crystal lattice is sheared. This will cause the atoms to form a spiral structure around her central discoloration line. So let's talk about the structure of mixed discoloration. So in a mixed discoloration, both edge and screw opponents coexist along different sections of the same discoloration line, and the discoloration line may curve or tilt with different parts behaving as edge or screw discolorations depending on their orientation. So I'd like to talk about Burger vector. So yeah, the Burger vector is a crucial concept in discoloration study. Before we go more deep, we have to understand the general things like what is Burger vector. So Burger vector is defining the lattice distortion of magnitude and the direction. It's a conserved quantity along the discoloration line, remaining constant despite changes in direction or shape of the discoloration line. Like to slide about what is the effects on the material properties. Alright, discolorations, including mixed discoloration, enable plastic deformation in crystals by allowing atomic plans to slip past each other with less energy, and they can interact with other defects also, such as vacancies and grain boundaries, to influence material strength, hardness, and fatigue resistance.